Hello everyone, my name is Jun, and today I will present our work, the next best view prediction for the active stereo cameras and highly reflective objects. So the reliable depth data acquisition is an important problem in many robotic applications, like the bin picking and the 3D reconstruction. And for the indoor application, the active stereo camera is widely used because of its high accuracy. And this camera, like the RealSense, is equipped with a light projector for simplify this stereo matching problem. And this camera can sense reliable depth data when object has matte surfaces. However, one challenge is a missing depth measurement for the reflected surfaces, like the metallic parts. And this is generally caused by the specular reflection, because the light is either directly back to the camera, causing this image saturation, or reflect to a separate direction, completely missing the camera, causing this low SNR. And to solve this problem, in our previous work, we developed a depth filter method. However, the acquisition of this active stereo camera is generally slow, and capturing the large number of viewpoints is not practical. And therefore, in this work, we propose a next best view approach for shiny objects. And in particular, we first model its specular reflection and then estimate the prior information of the objects. And finally, we integrate them into an Activision framework for the next best view prediction. And here we first show this depth acquisition process for the active stereo camera. So when the light hits on the object surfaces, the camera first receives the reflected light. And given the known exposure time, the camera can map the total exposure to the image intensity. And finally, the depth sensing probability can be estimated from it. And in the real world, both diffuse and specular reflection exist. And to model this, we use a Phong reflection model. So the E is a total radiance received by the camera, and the KD and KS are the diffuse and specular reflection parameters. And to estimate them, we use a two-stage least square method. So please check our paper for more details. Here, just show a few examples of our estimated Phong parameters for the different objects. So we can see that for object with the reflective surfaces, its specular parameters are higher than the matte objects. And for an active stereo camera, if the pixel is too bright or too dark, the depth missing problem will happen. And therefore, we need to map the radiance to the pixel intensity. And to achieve this, we use a photometric response function. And the depth sensing probability can increase with its pixel intensity and quickly drops to 0 if it's saturated. And for our reflection model, the surface norm and the depth hypothesis is required. And to get all this information, we take the advantage of our object CAD model and use an RGB-based pose estimator. So given this predicted object pose hypothesis and the CAD model, we can have the prior information of the depth and surface norm, and then compute its information gain for the next best view prediction. So in our experiments, we use a sensor camera and they evaluate our NBV pipeline on the raw dataset, which was captured using this sensor. And we test our NBV approach against the two baselines. Here, just show the performance of as the accumulation of the viewpoints. We can see that our approach requires much fewer viewpoints and to achieve the same level of the depth completeness. However, there are some unresolved problems, like the interreflection, which is not modeled here, and are expected to be solved in the future work. And thank you for listening, and I would like to take questions.